One of the main advances and one of the main things proven in the 19th century deals with the solvability of polynomial equations. That is, finding the roots of a given polynomial. And we've already seen this before. We've already seen, we know how to solve quadratic equations. That's been known for a long time. For cubic equations, remember we saw what Cardano did. He sort of looked at the so-called depressed cubic and was able to solve that. We also saw what happened to quartic equations as well. Now, the next obvious question is, what about quintic equations? When can we find solutions to a fifth degree equation? And I think we have to first understand even what we mean by find solutions or find a formula for a solution to a fifth degree equation. So if we think about the solutions that we've seen so far, solutions for quadratics, solutions for cubics, and solutions for quartics, the formulas are all given in terms of the operations that we can do on the field of rational numbers, that is add, subtract, multiply, divide, and then also by extracting various roots, so square root, cube roots, fourth roots, that sort of thing. And then combinations of those as well. So maybe the square root of a cubic root, or a cubic root or of a square root, or however it comes up, right? But just doing those 5 different things, like if you think about a 4-function calculator usually has 5 functions: add, subtract, multiply, divide, and square root. It's like that, but instead of just square root, we can take all of the roots that we want to, all of the integer roots that we want to. Okay, and so for any polynomial of degree 1, 2, 3, or 4, we can always express the roots with a formula in terms of those operations. Okay, so the question then becomes, what about a 5th degree polynomial or 6th degree polynomial? Are there ways that we can find a formula for the root of for the roots of a general 5th degree polynomial? Well, one of the things that would involve, let me adjust this for a second. One of the things that would definitely involve, if there was such a way to do that, is we'd have to be able to express the roots of these polynomials, the roots of a 5th degree polynomial, of a general 5th degree polynomial, as just these 5 functions. The 4 functions of add, subtract, multiply, divide, the 4 field operations plus root extraction. If we're not able to express the roots using those, then we cannot have a formula for solving higher degree polynomials in the sense that we meant. And that is the sense that's meant, getting a formula for it. Now you can always, sort of make up your own function and call that the formula, but that's not really what we're talking about when we talk about, getting a formula for the roots of a polynomial. So I want to explain just a little bit. I'm gonna not even scratch the surface on why we cannot get a general formula for the roots of a 5th degree polynomial. Okay, but before I do that, I'm gonna have to give a little more background information on fields and field extensions and polynomials and this sort of thing. So I need to grab my notes actually. Okay. So let's begin just by setting some notation. So we're going to have Q. Q, is the set of rational numbers. So Q is a set of rational numbers, standard notation there. And then we can look at the following. We can look at the field, or the ring of polynomials with coefficients in Q. So these are going to be polynomials of the form a0 plus a1x plus ... plus an xn. Again, I'm going to erase this because I'm going to need to use this. So we want to look at polynomials with coefficients in Q. Okay, so we're going to look at polynomials with coefficients in Q. Okay, we can also look at other fields as well, like real numbers or finite fields or something like that. Okay, so what we want to do is we want to think about polynomials in Q that have no roots in Q. So this is kind of where everything comes from. So if we have, let me just back up and say all of this is kind of going with the goal of explaining why there is no formula for finding the roots of a 5th degree polynomial. So then what we want to assume, the 5th degree polynomial we want to assume we're dealing with is irreducible over Q, meaning it has no root in Q. See, if it had a root in Q, we could take the polynomial, divide by x minus that root. That would give us, x minus that root times the fourth degree polynomial, and then we know a formula for the roots of the fourth degree polynomial. So we want to think about polynomials that are irreducible. Okay, so if I over Q, that is, it has no roots in Q, and then how we can build fields. So Q is a field. Okay, how we can build fields that extend Q that are kind of just small enough, or just big enough to include roots of the equation, or the polynomial that we care about. Okay, so I'm going to begin with this example, P of x. We're going to look at two examples. P of x is equal to x squared minus 2. Okay, now one thing that we have to keep in mind when we're doing this is we have sort of two perspectives that we need to keep in mind. On the one hand, we know about real numbers. We know about real numbers, and so we know that the roots of this polynomial are plus or minus square root of 2. But as far as Q is concerned, as far as this field Q is concerned, it doesn't know about the square root of 2. Okay, so we want to keep things sort of algebraic here and not think so much about using Euler's method or something to think about what the root of a polynomial like this would be. So we want to think about living in Q and then how we can sort of abstractly build fields on top of that are going to give us roots, that are going to have roots of polynomials like this, or whatever we're dealing with. Okay, but we also, just for psychological purposes and for notational purposes, we also do know that there is a real number called the square root of 2 that satisfies this equation, and minus the square root of 2 that satisfies this equation. Okay, so what we want to do here is this is irreducible over Q. This is irreducible over Q, meaning there's no rational solution. Now, by the fundamental theorem of algebra, we know that there are two roots to this equation. We don't know what they are yet because we're only thinking about rational numbers, but we know there are two roots of this equation. Okay, so what we're going to do is the following. We're going to extend Q to a larger field. And we're just going to say, let's say there is this element theta. And what is theta? The only thing I know about theta is theta squared is equal to 2. Or equivalently, theta squared minus 2 is equal to 0. And now I'm going to extend this field. And this field is going to look like the following. My new field, which for now I'm going to call F1, and I'm going to give it another name in just a second. This is going to be all elements of the form A plus B theta for A and B in Q. Okay, right now theta is just a symbol. We don't know what it is, right? I mean, we know, okay, that it's the square root of 2, and we know a lot of things about the square root of 2, but if we're just thinking sort of algebraically, starting from Q here, the only thing we know about theta is that it satisfies the equation theta squared minus 2. And so now we have these, I'm saying this new set here, I'm saying it's a field, so if it's a field I have to tell you what it means to multiply elements and stuff like that. So if we have two elements, we're going to do A1 plus B1 theta plus A2 plus B2 theta is going to be the exact thing that you think it is, which is A1 plus A2 plus B1 plus B2 theta. B1 plus B2 theta. Okay, and then this is clearly in the field because this is a rational number and this is a rational number. Okay, maybe let's look at what it means to multiply two elements. Okay, so we're going to multiply two elements. Well, when we multiply two elements, we're just going to FOIL this. So A1 times A2. So we're going to have A1 times A2. Then we're going to have A1 So we're going to have A1 B2 theta. So A1 B2 plus B1 A2 theta. And then finally we're going to have B1 plus B1 B2 theta squared. Okay, and my contention is that this is in that set. Why is it in that set? Well, what do you have to do to be in this set? You have to be equal to a rational number plus B times theta. Well, A1 times A2, that's rational. That's a rational number times theta. And then what about this? B1, B2 theta squared. Well, the only thing I know about theta squared is that theta squared minus 2 is equal to 0. So this theta squared is really 2. And so A1, A2 plus 2, B1, B2 is a rational number. And so to make it look more like what we have up here, we can write this as A1, A2 plus 2, B1, B2 plus A1, B2 plus B1, A2 theta. This is a rational number plus a rational number times theta. And so this is our field. Okay, now, of course, let me back up a second and say, well, we know what theta is. Like, we have notation for exactly this. We know what theta is. Theta is simply the square root of 2. And if we're allowed to use real numbers, this is exactly how we would write things. And so we get something like this. But here's an important point. From the perspective of Q, there are two roots of this equation, plus and minus Q. And from the perspective of Q, it cannot distinguish between those two. So in other words, I could have defined it like this, or I could have given this minus the square root of 2. And I would have gotten something very similar here, just with, instead of that, I would have gotten minus the square root of 2. Okay, so this is an important concept. From the perspective of Q, these two roots are combined. The Q cannot split them apart. Now, this field right here is called the splitting field for this polynomial. The roots split apart. And inside F1, we can distinguish between these two roots of Q, between the positive square root of 2. I think I said between the square root of Q, but I mean the square root of this polynomial, between the positive square root of 2 and the negative square root of 2, which we know from real number theory and stuff like that exists. Okay, another thing that this is called is this symbol right here. It's Q adjoined with theta, or Q adjoined theta. Okay, it's basically the smallest field like this that contains theta. Okay, so now let's look at another example. And we're going to come back to this example as well, because there's other properties about this example that are very instructive. So now I'm going to come over here and make what appears to be a simple change, which is x cubed minus 2. Sorry, I emphasized the wrong thing. It's x cubed minus 2. The minus 2 stays the same. The new thing is that we have a cube there instead of a square. So let's try to do something similar to what we just did, and see if it works. Okay, well, where works means, well, we'll see. Okay, so again, I'm going to think about adding an element theta. Of course, I know I want the cubed root of 2 here, right? We know that, right? So I think about adding an element theta, and the only thing I know about theta is theta cubed minus 2 is equal to 0. Okay, and I'm going to do this in a couple of steps because there's going to be a couple of different things that I need to go through. Okay, so now I'm going to look at F1, and I just want to tell you right now, the thing that I'm about to write is not going to be a field. So we're going to have to modify this. Okay. So it's going to look, if we sort of again reason with analogy to what we did over here, we're going to have A plus B theta, where A and B are are rational numbers. Okay, and so now the question is the following. Does this form a field? Well, I will let you show that if you add two elements, you're going to get another element in this field. So as a matter of fact, I didn't say this before, we can think about this as a vector space where the basis vectors are 1 and theta. And this is always going to be a vector space, but as we'll see in just a minute, it's not going to be a field. Okay, I want to make sure that everything is showing up well. Okay, so why is this not a field? Well, let's just look at a very simple case. You could look at, a1 plus b1 theta times a2 plus b2 theta to get something more complicated. But let's look at the very simple case where a1 equals a2, and they're 0, and b1 and b2 are both equal to 1. So then we're going to have b1 theta times b2 theta, and the way that we want to define multiplication is exactly like how it should work with real numbers or irrational numbers. So this should be equal to b1 b2 theta squared. Now in the previous example, we knew that theta squared minus 2 is equal to 0, so we knew that theta squared is equal to 2. But that's not what we know here. We only know theta cubed minus 2 is equal to 0. So theta squared is not in this set right here. So if we want to make this work, we can't just do theta here. We also need to add theta squared. Okay, so we're going to be let me write it cleanly again. We're going to have a plus b theta, plus c theta squared, where a, b, c are rational numbers. Okay. Now here what we know, and I will let you verify this for yourself. It's going to be sort of a lot of tedious algebra, or not a lot, but some tedious algebra. This does define a field. If you think about what we're going to get when we multiply two elements together, we're going to get things that we can compute. Okay, we're going to get either theta squared. When we do this, we're going to get theta times theta squared, which is theta cubed, and theta cubed is equal to 2. We're going to get theta, which is just theta, or we're going to get theta to the power of 4, and theta to the power of 4 is simply theta to the power of 4 is theta cubed times theta, and theta cubed is equal to 2, so that's 2 theta, which is in this set here. Okay, so I will let you work out the details that this does define a field. Okay, now does this contain the roots of P? Does this field contain the roots of P? Well, the answer is no. It does not contain the roots of P. So what does it contain? It contains one root of P. So theta, by definition, is one root. So in this larger field, we can factor this polynomial in the following way. We can factor this polynomial as x minus theta times x squared plus theta x plus theta squared. But this piece right here is irreducible over this field. So this is a field, and it gives one root of this polynomial x cubed minus 2, but it does not give all of the roots of this polynomial x cubed minus 2. Here's what's missing. So before, remember what we got. We got the plus and minus. When I said before, when we looked at the polynomial x squared minus 2, we got the plus the square root of 2 and minus the square root of 2. Whenever you have a quadratic, so let's think back to sort of high school algebra. When we have a quadratic, whenever we have a quadratic over the real numbers, we know that if there's complex roots or if there's non-real roots, they always come in complex conjugate pairs. A plus bi, a minus bi. Okay, if we have a polynomial with rational coefficients, we know the irrational roots always come in conjugate pairs as well. So if you have a polynomial and we know it has rational coefficients and we know a plus b times the square root of 2 is a root, we know a minus b times the square root of 2 is also going to be a root. That's the conjugate. Okay, so before a, we know that the plus square root of 2 is a root, and so we know minus square root of 2 is also going to be a root. It's only necessarily true if we know that the roots of the polynomial are rational numbers. Okay, so now we have something similar but a little more abstract. We have x cubed minus 2. This is irreducible over q. And so there is a generalization of this idea of conjugate roots. There's 3 different roots here for this polynomial, for this irreducible polynomial. They're all indistinguishable over q. In other words, q can't tell them apart. It just knows its roots to this polynomial right here. And so we say they're conjugates. Okay, now we're just taking some root theta here, and coming up, making a field, that sort of the smallest field that contains that root. And now in that field, we have this root, but we still have these roots right here. And so with respect to this field, F1, there's 2 roots of this that would also be conjugate. And so things get more abstract. So before, what were the differences? Well, you had square root of 2 and minus the square root of 2. So notice what we're doing here. The number minus 1 is a second root of unity, meaning minus 1 squared is equal to 1. Okay, so if we, just to write down what we were talking about before, if we do minus 1 times square root of 2 squared, well, minus 1 times minus 1 is 1, the square root of 2 times square root of 2 is 2, and so we get 2. So it's not just theta that we needed to add. We needed to add theta times all of the second roots of unity. But theta is just, it was the square root of 2, and the second root of unities, the two roots, the second roots of unity are just plus and minus 1, and those are already in Q. So we didn't have to do anything else. But here we have other roots of unity, which we can express in complex notation using complex numbers. R is equal to 2 pi I over 3. These are the third roots of unity. So we also need to add this. We also need to add these roots. Okay, but now if we think about what's going to happen, if we add these roots to this list up here, did like a plus d times r and that sort of thing, we're also going to need to know what r times what r squared is, what r times theta is, and all of that sort of thing. Okay, so one way that we can do this is we can call this F1. And now for F2, we can say F2, this right here would be Q with we would say something like this, the third root of 2 appended, or adjoined. Okay, so then F2, we could say is going to be equal to F1 if we adjoin the third root of unity. I'm going to call this R sub 3, the third root of unity. Okay, now we need R and R squared. R cubed is equal to 1. So what I'm saying is this right here is going to be elements of the form A plus BR plus CR squared. Just assume there's a 3 there, so we know it's the third root of unity, where A, B, and C are in F1, are in this field. And now for each one of these A's, for that A, we're going to write it in this form right here. And for this right here, we're going to write it in this form. And for this right here, we're going to write it in this form. And then when we do this, we're going to get the following. Is going to be equal to A1 plus A2 theta plus A3 theta squared plus b1r plus b2r theta plus b2, b3 r theta squared, where all of the a's and all of the b's are rational numbers. Okay. Now, this is not the typical notation that we would use. So maybe I'm going to call this f1 prime, and then I'm going to call this f1. The reason I say it's not the notation that we use is because the extension of f1 prime over q does not give us all of the roots, all of these roots right here. So we have appended a radical. So theta cubed minus 2, this means that theta is equal to the cubed root of 3. Okay, so we've appended a radical, or we've adjoined a radical, but we haven't gotten all of the roots of the minimal polynomial that it satisfies. Okay, and so to do that, we need to add these roots of unity as well. And so then this right here, f1, in the typical theory that we'll get to in just a minute, is called the Galois extension of f. Or sorry, it is a Galois extension of q. Okay, and again, what we mean by that is you append a radical, and then the minimal polynomial of that radical, that new field has all of the roots. Before f1 prime just had one of the roots. Okay. All right. So a very important thing, and again, man, this is such a huge topic. I'm just going to be able to say some words about it, and maybe you guys can sort of think about more things about it. But we're going to talk a little bit about symmetry, and I've hinted at this before. So again, I want to go back to this example. If you look at x cubed minus 2, and we think about the roots, we can sort of think about things up here because we know about real numbers and all of this sort of thing, right? And we know that the roots and complex numbers, and so we know that the roots of this are going to be of the form r times the third root of 2, r squared times the third root of 2, and the third root of 2, where r is the third root of unity. Okay, so let me just say explicitly, since we have the benefit of not being restricted to q, we know that the roots of this, we could say theta 1 is equal to the third root of 2, and of course, sorry, I got this backwards. The third root of 2, and even this symbol right here, we're picking the real number to be the real positive root here, and that's the only one. And then we're going to have e to the 2 pi I over 3 times this, and then e to the 4 pi I over 3 times that as well. Okay, so that's theta 1. Let me even write this out a little bit more clearly. So that's theta 1, and then we could say theta 2 is equal to e to the 2 pi I over 3 like this, and then theta 3 is equal to e to the 4 pi I over 3 like this. So now again, we can distinguish these roots from each other, but the field Q can't. They're all just roots of this polynomial right here. But other than that, there's this symmetry. There's nothing different about them. There's just this symmetry. Okay, so what this tells us then is that if we can permute these roots here, and Q's not going to know the difference. Like if we permute these roots, and now we say, okay, theta 1 is equal to this one, theta 2 is equal to that one, and theta 3 is equal to this one, or however it goes. Okay, we can see that there's going to be a difference, but Q over here doesn't detect a difference because it doesn't see how these roots are different. They're not split in Q. Okay. Um, that is okay. So that is going to be a very important thing. So I want to mention one last thing before I end this video, and then go on to and then sort of finish up in the next video. When we say that an irreducible polynomial is solvable by radicals we mean there is a tower of fields Q. Q is going to be contained. It's going to be a subfield of F1. This is going to be a subfield of F2, all the way up to a field Fn that we're going to be called K, such that basically two things are true. One, K contains all roots of P. So typically we want to think that K is what's called the splitting field, but it could be larger than that. But the point is that it includes all the roots. And two, to go from Fk to Fk plus 1, we simply adjoin a radical. So in the examples we've seen, we've adjoined either the square root of 2 or the cubed root of 2, and if needed, and I'm going to write this as ROU, roots of unity. If we need to, we have to add the roots of unity. Okay, for the example for x squared minus 2 equals 0, we did not have to add the roots of unity because Q already contains the roots of unity. Okay, for the x cubed minus 2 equals 0, we did have to add the roots of unity because Q does not contain the third roots of unity because they are non-real. They're non-real numbers. They're complex numbers, and so we have to add them. Okay, and so in general, so in the last example, we got this field F1, which we got by adjoining the third root of 2 or a third root of 2 and the third root of unity. Now, if we wanted to now adjoin another third root, we would just have to adjoin that third root, and we would not have to adjoin the roots of unity to go to F2. Okay, so what we have here is going from Q to K. Each one of these fields is just an extension of the previous one, and this very simple way by adding a radical and perhaps the roots of unity. And what we're going to see in the next video is that these extensions have nice properties, and if we have a set of things like this with nice I guess the important thing is to say these extensions have a nice property, and what we're going to show is that there's a fifth degree polynomial such that there is no set of extensions that have this nice property, and therefore there can be therefore for that polynomial, not for all polynomials, all fifth degree polynomials, but for that polynomial we cannot solve it with radicals. But I'm going to talk about that in the next video.